because, yeah, I felt for the sake of coherence. Okay, so let's continue. So there were some nice questions that I think are serve for everyone. So what I meant by this SO1, 1 over here was that the isometry, so what are the manifest isometries of the static patch? But it's upstairs now. It's no good? Okay. Okay, back in the spaceship. So notice that there's a manifest isometry here, while there's the SO3, and these will play an important role when we characterize the representations of the group, yeah? So that's why I want to emphasize. And what I mean here is that this time translation symmetry, T goes to T plus A. So notice that this patch of the de Sitter has an isometry which is time-like. But the global spacetime does not, because this isometry that translates times in the static patch becomes space-like outside of this patch, and then time-like again, and then space-like. Okay, so the killing flow is not everywhere time-like, and in fact one can show that there is no global time-like killing vector in this space. And I should say that although I emphasized before that many FLRW spaces have horizons, what distinguishes the de Sitter horizon from other horizons, cosmological horizons, is that this one is truly static, yeah? The region inside of it admits this very static representation, and that is a special feature that we can't expect in generality. So in a sense, it's sort of a rather equilibrium type of portion of space-time, yeah? And that makes it very nice to work with because it gives us a little bit more of a theoretical handle. Now, let me say, okay. I think that's, okay, so let's proceed now to a question that was already anticipated, yeah? And discuss the nature of the theory a little bit more broadly, of the classical theory a little bit more broadly. So, like we said before, these are very rich equations, and so there's no reason why they would admit a unique solution, and in fact, they generally admit an infinite number of solutions. And so I'd like to discuss the character of these solutions in a little more detail, because it turns out that there is a nice way to characterize the late time structure of these solutions. So the late time structure and to do so, I'm going to introduce a coordinate which is sometimes called the conformal clock, which is very useful. And maybe it was written in the inflation talks, but let me introduce the following coordinate, eta, which ranges. So for the flat slicing of de Sitter, let's take eta to range from -infinity to 0. So the far future is when eta goes to 0 along the negative real line, yeah? And
sorry, Dio, can you change the chalk color?
The chalk color
for the audience?
Yes. Is this better? Maybe not. Is this better? Thank you. Okay. So, although we cannot solve these equations exactly, that would be a remarkable achievement, we can classify their behavior near this double pole. Yeah? So the following property is satisfied by solutions to these equations. Namely, they admit, and this was uncovered in early work of Starobinsky, followed by, I believe, followed chronologically by more mathematical work of Pfeffman and Graham in the context of hyperbolic spaces, but the properties are similar. But you may be familiar with this in ADS, but I would like to emphasize the differences in what follows. I think it's 2. So one has a small eta expansion, yeah? So late time expansion of the solution space. Okay? So this is an expansion for small eta. And what's important is that the expansion, it converges with a small but finite radius of convergence in this parameter eta. And the data of the solution, yeah, is given by a general 3-metric along the Cauchy surface. Yeah, so imagine we have a spatial Cauchy surface endowed with some topology. It doesn't have to be the topology of an S3. It can be a more general 3-manifold. Yeah, so there's 3-manifold that we specify. And on this 3-manifold, it could even be a 3-manifold that has exotic properties, many handles, maybe even boundaries. Anyway, some 3-manifold. And we endow this 3-manifold with a metric G0, yeah? So that's the data that lives on our Cauchy slice. And this G2 over here is fixed entirely in terms of G0. If I remember correctly, it's something like the Ricci scalar of G0 minus, sorry, the Ricci tensor of G0 minus the Ricci scalar times G0. This is sometimes called the Schouten tensor. So it's fixed. It's not independent data. It's fixed entirely in terms of G0. And then there's this independent data G3, yeah, which has the property that it is a tensor that is conserved and traceless with respect to index contraction of G0. Yeah? So this is independent data, and you can view this roughly as the conjugate variable to G0. Yeah, so you have the position and the velocity of your phase, gravitational phase space, and we can do a little counting problem. Yeah, so these are 3 tensors. Yeah, so how many free degrees of freedom do we have? So how many independent components? Well, symmetric 3 by 3 has how many independent components? 6. And there are how many constraints? So there's 4 constraints. Yeah, so the trace and the divergence. So then we have 6 minus 4 is 2. Yeah. And similarly, this is a metric modulo the diffeomorphisms. Yeah. And also modulo the redefinitions of the slice eta. Yeah. Ah, sorry, white chalk. My nemesis. Yeah. Okay, so we have 2 independent variables here, and here we have also 2 independent variables because of the 4 coordinate maps. Yeah. And so our phase space naturally has 2 + 2 degrees of freedom per spatial point, which are the cosmological version of the fact that the gravitational field has 2 polarizations, or 2 independent degrees of freedom, yeah? And so this captures then, non-linearly, the full late time, or a large portion of the gravitational phase space, at least that which expands indefinitely, of these equations. So it's a remarkable thing that we can characterize a large portion of this. Of course, the problem is that when we go into the past, the coordinates can break down, or it can even develop, and it rather generally will, it can develop singular behavior, yeah? So nothing guarantees that such future configurations will evolve in the past to a smooth space or to a bounce. In fact, generally it can develop cosmological singularities, and this is rather generic thanks to theorems of Hawking and others. And of course there's the time reversal of this, which is that if you start with data in the far past and evolve it, often it will develop the big crunch singularities, yeah? So the gravitational phase space will not, even if the topology is S3, if you put enough gravitational energy or bend the metric enough, it can easily flow back to a singular. And so this is part of the issue that we were talking at the beginning, that you have these UV problems. So you can develop cosmological singularities, similarly in the future, yeah? But there are some theorems about the classical stability of the space-time which are important to note, which is that if you are so these are theorems of the type, I'll give you the spirit of the theorem, that if you happen to be sufficiently close in some small but finite neighborhood near the pure de Sitter configuration, which has this equal to the round S3, yeah, perfectly round S3, and this is some simple tensor as well. If you're sufficiently close to that data set, then small deformations will not disrupt the causal structure of the manifold. In other words, it will retain this bounce-like structure. So there is a small but finite phase space that keeps it like a bouncing cosmology, except now it will generally be some more wobbly bounce. Yeah? In other words, yeah. It's an analogous of that, but I would call it a stability theorem. Yeah. The cosmological stability theorem, that there's nearby, sufficiently close, there exists a finite neighborhood of deformations of the Cauchy data that deform the space without disrupting the integrity of its causal structure. Yeah. And there are also other theorems which are a little more elaborate, that depending on the type of topology and the fundamental group of the manifold you have over here, sometimes it's guaranteed that you'll develop singularities. For instance, if you have non-trivial cycles, often one develops sort of singular points. This is most easily seen over here. If I take a quotient of R3 into a torus, yeah, as eta goes to infinity, the cycles shrink to a point, and you have behavior that's somewhat singular. And so it's important to appreciate that this phase space, the gravitational phase space, and although the theorems are often stated for the pure gravity theory, one expects similar statements for matter fields, provided they obey null energy conditions and things of that type. There's a rather rich gravitational phase space at the classical level, yeah? Which is one of the big puzzles of cosmology, because if the space-time develops singular behavior, we need to complete the theory, yeah? It will start activating all of these terms, these higher curvature terms which are ordinarily suppressed, will start getting activated by the development of the singularity. And this is a singularity that a priori is not shielded by a horizon. It's a cosmological singularity.
Yeah.
Yeah.
Question here. Here.
Yeah. Yeah.
If you are at late times and you have matter, but it's sufficiently diluted, does this still hold?
If you have?
Matter, but it's sufficiently diluted.
If you have, yeah, so one, I think it still holds, although I wouldn't be able to quote to you a precise mathematical theorem. The general expectation is summarized in what's called the cosmological no-hair theorem. Which states somewhat in the opposite direction that a large class of initial data on the Cauchy surface, provided the extrinsic curvature is positive, which is an indicator of expansion, will evolve in such a way that any finite proper volume at late times will look indistinguishable from the pure de Sitter. And this you can see because although this metric has many features, the proper metric has the 1 over eta squared in front. So they're stretched in proper units over a parametrically large portion of space. Yeah? And so it irons out. These features are preserved globally. So if you could be able to see this infinite volume, you would be able to retrieve the classical information. But it becomes extraordinarily hard for any reasonable experiment to do that. And from the point of view of the horizon, what this means is a little like the no-hair theorem of the black hole, that you're sitting here and all of these features, yeah, are just redshifted and washed away from your space-time. And so you will perceive eventually the behavior of this featureless empty static patch at late enough times. Everything has fallen through your cosmological horizon. So the dynamics are quite remarkable in that regard. Yeah. Good. Now, although generally solutions are not known, actually, I like to point out that there is an example, a family of exact solutions that are non-pure de Sitter that are known. Sometimes they're called the Taub-Nut de Sitter bounce cosmologies. And they're a lot of fun to play with. But just to give you an example, an actual example of a solution, a global solution to these equations, you can take the following. So this is a solution, and if you have access to Mathematica, which I told you do, you can check, I was told you do, you can check, let me write it down just for the matter, as a matter of principle, that it exists. I'll explain in a moment what these are. So this over here, where f of tau is the following. No puedo. Is yellow, does yellow work? No? No. Yes. Yeah. Okay. Alan is not allowed to speak for the students. So I like this. Okay, of course the details are not important for our discussion, but it is important to see an actual solution. I think that's non-de Sitter. And so this over here is a solution. These are the one forms of SU2. So this, for example, is the two-sphere. So this is the round two-sphere, and this is the other one form of SU2. And when when D naught and C naught are constants, and when they're equal to, I think, 1 and 0, you retrieve the pure de Sitter solution, and you can vary them slightly, and that will deform the pure de Sitter solution. The topology of the Cauchy surface is a three-sphere, so if you take constant tau, the topology is an S3. The geometry is not the round S3, it's what's known as a squashed three-sphere. And you have a tau ranges, at least for D and C, close enough to 1, 0. Tau ranges between plus infinity and minus infinity. You have a bounce a wobbly bounce. And as you crank up the values of D naught and C naught, you see that you actually develop a singular behavior in the past. Yeah, it's a very, very explicit, concrete example of probably a large character of solutions to these equations, these complicated equations. Yeah, and so that's an example. And the other, and the other point I want to make about, so I emphasized a few times similarities to the black hole, but I'd like to emphasize an important difference. And this will be the sort of the comment, one of the final comments I'll provide regarding classical behavior. Yeah, which is the statement, so I'll give you a physics explanation, but the statement stems from a rigorous mathematical theorem in a paper of Gao and Wald, who were trying to understand the nature of time delay and advance in general relativity, whether we can find ways to sort of have geodesics approach a point in a faster and slower way by distributing matter in a certain field. And one of their corollaries for the case of de Sitter with closed, so crucially with a closed Cauchy surface, so they assumed a generic solution obeying the null so you have some closed Cauchy surface, 3 surface, and you have some matter. So now you're exciting it slightly, but it could even be a gravitational excitation that obeys the null energy condition and a slightly more technical version of it, which is called the null generic condition. But effectively, the statement translates to the fact that upon deforming with this null energy obeying matter, the de Sitter space-time, the pure de Sitter space-time, a geodesic, the past light cone of a point sufficiently far into the future will intersect at a finite time the complete Cauchy surface. Yeah, so this is the statement. So let me draw a picture. What it effectively means is that generic deformations of de Sitter stretch the Penrose diagram in a vertical way such that your past light cone will intersect the complete Cauchy surface before, well, let me draw it, let me make the point more clear, before reaching future infinity, which is to be contrasted with the de Sitter Penrose diagram, where you intersect the complete Cauchy surface only at this very special point at future infinity. And it's a way of expressing the fact that matter generally contracts an expanding spacetime. So it brings it closer together, and that has the effect of giving you causal access to physics that would have otherwise been out of causal contact. So in other words, from the point of view of this static patch, you see here, if you have an entity on the other side sending signals along this world line over here, you will never receive these signals. But if you deform the space-like slightly to this space-time, the signals sent for some time of this other side, will reach your world line. You will have access to the other side. And this contrasts rather sharply the behavior of a black hole. So just to give you the analogous situation of a black hole, where, of course, the empty Schwarzschild Penrose diagram, well, Minkowski or ADS, it doesn't matter, signals never reach you, and the effective matter has the effect of bringing in the horizon and effectively stretching the Penrose diagram horizontally. Yeah? So actually, the signals reach you even less. Yeah? So the effective matter is to decorrelate the two sides for a black hole, whereas in this case, it actually adds connectivity to the space-time. And so when we think about the analogy to black holes in the context of cosmology and cosmological horizons, we should be cautious with our analogies and interpretations because the dynamics of the two can differ significantly. Okay? So this simple result, I think, illustrates that point. And this is a point that we use in inflation often because in inflation, I don't know if it was discussed, we have this idea of the re-entering of super horizon modes. And this all has to do with a game being played in the causal structure of the expanding spacetime and when things can be outside and back inside the past light cone. That's just a side remark. But okay, so then to conclude, so let's take stock of where we're at. So I tried to motivate, in broad terms, the necessity for theory of cosmology, and that it's not just a classical problem, but also a quantum problem. And then we thought a little bit about how to quantify cosmological spacetimes in a very simple terms, these FLRW metrics, and we explored the possible behavior of scale factors. And then we noted that essentially, due to the non-diluting nature of the cosmological constant, we have a dominant source of energy at sufficiently late times and large distances, which gives it attractor-type behavior in cosmology. And from the point of view of effective field theory, one can say this is an expression of the fact that this is the relevant most term in the effective Lagrangian, the cosmological constant term. And we studied then, we decided as a theoretical idealization, but also due to phenomenological reasons, we started to study the nature of such a theory at the classical level. We exhibited its in the analytical solutions in their maximally symmetric state. We identified this isometry group, yeah, and its various subgroups. And then we discussed a little more broadly the classical configuration space of the field and the different phenomena of solutions, including bounces, big bangs, big crunches, and things of the like. And finally, I gave a cautionary word about comparing and contrasting the behavior of black hole horizons to their cosmological counterpart. All right. So what I'd like to do now is pause first and see if there are any questions. Yeah.
Thank you. So here you're saying that if you had a flat slicing, you would have a singularity.
A flat slicing? No, so flat, well, it depends if it's compact or not. So this space is non-singular. Yeah? So the eta going to infinity is a coordinate singularity, but not a physical singularity. And what this space captures in the Penrose diagram is this portion over here. So constant eta slices are these slices over here, and eta equal to minus infinity is the following null slice over here. And eta going to 0 is this slice over here. But I can smoothly continue the space to this patch over here, and therefore this is a coordinate singularity. However, if I identify this into a torus, then I no longer have this causal structure, and I've lost this point at infinity, and the discussion becomes different, because now the proper size of the cycles of the torus tend to 0. And I have a universe that really shrinks to a point. Yeah. So this is flat slicing, but I've done something more because I made it a flat torus.
Just to have it compact?
Yeah, in fact, not even only one of the, even if one direction is compact and the other are non-compact, so S1 times R2 already is sufficient for this phenomena.
But the theorem that you said that you can change a little bit the
So this was for
deformation?
compact. This was for S3.
only for S3.
This was for S3, indeed. That was for S3 is the most clear statement of the theorem. Generally, one wants to avoid these kind of situations with the points at infinity, and so it's easiest to formulate these statements in the compact case. If not, one has to supply additional data on the behavior of fields and things like that at points at infinity.
So you can say nothing about
I'm
something
not sure.
like a flat slicing.
I can't quote a theorem for you. Maybe people have said things, but they would have to be sensitive to things like the behavior at spatial infinity of the fields and things of that sort. It's an interesting question. Yeah.
Okay, thank you.
Yeah. Other questions? Because we're going to change gears now. And so I want to be sure that we get this out of our system.
I have a question.
Yeah.
I want to ask if there is another aspects that you can understand in the comparison of the Schwarzschild solution and the static patch, and in this playing of changing R to 1 over R, they're very similar solutions, and they take. The picture that I have in my mind is you are outside the black hole, and the others in the other solution you're inside. But there is a 2 that kind of ruins that that picture. But this captures that. This that you explained captures that relationship, in the sense that when the black hole grows, then the event horizon eats part of my Cauchy slice, so I have less. In the sitter, it's exactly the opposite. If you perturb the system, the event horizon gives you more space, and that's why you have more.
Yes.
But and that is captured by the idea of the being outside and inside the black hole. But are there other?
You see, people, it's difficult because I would say the other way around. The equations are these, and you can choose the way to describe these equations, whichever way help. I like the idea that we're surrounded by a horizon. Energy falls through the horizon, it gets further away from us. Yeah, so, but it's difficult because these are words. I don't know what to do with them. The equations are less ambiguous.
Okay, yeah. Thank you.
Okay. Okay. Good. In that case, let me now proceed to make a few comments about the simplest quantum question we can ask in this space-time. Yeah? And the question is the following. Imagine that, in addition, so imagine now that we have a background which is given by the pure de Sitter solution. Yeah. So again, we'll start with the simplest version of the question, and on top of it lives some matter fields. Yeah. So, and that these matter fields are quantum fields. That live on the spacetime, but there's very small perturbations that to leading order, their dynamics occurs without disturbing the geometry itself. So we're working in a small G-Newton limit where the back reaction can be neglected for these fields, and they're propagating as if they were propagating in the fixed background. And we'd like to understand this sort of fixed background quantum field theory, and I'd like to make some general comments about the nature of this problem, okay? And the comments I'd like to make are sort of linked, I think, to points that I hope to have time to make later on. And so I'll take a slightly sort of more group theoretic approach to the problem. But now let me first start with some general remarks as to why this problem is somewhat different than the kind of problems that we're accustomed to when we study quantum field theory in Minkowski space. Yeah? So the one that is most prominently clear is that time translations are not present. And for that reason, notions that we take for granted in Minkowski and QFT, like the conservation of energy and things of the like, are no longer part of this space-time. You see, so the idea that I can organize my physical properties based on something like an eigenstate of a Hamiltonian or a conserved energy or the decay processes are constrained in that sense is not something we can generally assume. Yeah, when we have fields in this space. In fact, we can it's a very frequent phenomena in this space that you can have things like cosmological particle production, where out of the vacuum, we can have something that looks at early times like it has no particle content at all, but you wait long enough and you appear to have particles at late times. Yeah.
Case? Even in the static case?
In the static case, you will have other features which are dissipation. So in the static case, it's not even clear how to discuss a particle because it's an open system and things can fall through. And in fact, the best you can hope for are things like resonances, which have a finite width. And so we'll discuss that later on. But the more natural type of quanta in the static patch are things called quasi-normal modes, which are resonances that have a decay width, and they don't live forever. So you have other features in static patch. And also, from the static patch point of view, it's more natural to discuss the problem in the language of a density matrix rather than a pure state. And this density matrix has thermal features which could create excitations every so often that look like you've created a resonance thermally. So you have analogs of that. Particle and Guy covered some, but I think here I'm going to use a different language. So I won't be emphasizing things. I may make a comment, but I want to discuss it in a slightly more general sense, and I'll focus on heavy particles rather than light particles and things like that. Yeah. Gracias. Okay. Now. Okay, so, well, in fact, that's another point, that maybe we need to think about QFT with finite portions of space-time, yeah, which lead us more to questions about density matrices rather than pure states. And so this is something we may have to think about, yeah. But I think most importantly, the kind of observables so that we have in, for instance, Minkowski space, or even asymptotically ADS, which have the feature, so we can often construct gauge invariant or diff invariant, field redefinition, local field redefinition invariant. Observables, e.g., like the S matrix, which rest on the fact that in flat space we have a nice cluster decomposition principle. So if we go close enough to null infinity, things essentially separate largely from each other. We can build bunches of wave packets that are parametrically separated from other bunches and express the problem in terms of a nice asymptotically free Fock space that we take overlaps in the past and the future. So this kind of features, these features are absent in de Sitter space. Cluster decomposition is not something that the space-time obeys. Correlation functions can even grow spatially at late times, or they can decay very, very slowly. And so this idea that we can organize our Hilbert space in a way that has these nice features of the S matrix is not as simple. Yeah, and so these are big challenges. Yeah, so I mean the causal structure. In fact, already here, you sort of see that it's very difficult to decorrelate quantum features. And that's more explicit. Maybe you saw it in the inflation that you can have correlation functions that even grow logarithmically at sufficiently late time as you take them to Z, which is in violation of standard rules of cluster decomposition. Yeah? So there's some striking differences, and I'll come back to this, but let me anticipate it already, that if we activate gravity as well, we cannot forget about the constraints that are imposed by gravity, and that includes constraints of the diffeomorphisms. And from a gravitational viewpoint, the isometries of de Sitter, so this is an important point, so I'll say it twice maybe. These are coordinate transformations. That's a subset of the space of diffeomorphisms, which are gauge symmetries. They're gauge transformations of the theory. And so gauge invariant observables cannot transform under the action of a gauge symmetry. So this over here, then, has to be gauged in a truly diffeomorphism invariant theory. And so things that rely on space-time points are not diffeomorphism invariant because you've labeled them with a point. And so you may have to deal with that observable somehow to render it, or you may have to answer the question of what gauge fixed version of what gauge invariant calculation is such an object that depends on space-time points, a gauge fixed version of. Yeah? So these are all subtleties that we have to deal with. For the time being, we'll suppress the gravitational issue, but we'll come back to it. And but we do have at our disposal, and I think this is important, a large, at least for the fixed background case where we're not gauging it, a large isometry group. Yeah? And so we'll proceed and hope to be guided a little bit by the nature of this group. And so let me at least try to express what we could get out of this group, as it will play a role later on. So, and I think for the sake of simplicity, and because it bears some similarity, I'll exhibit some of the properties of the de Sitter group in its simplest instance, which is SO2,1, and then I'll tell you which parts of it carry through to SO4,1. Yeah? But what we can reasonably assume of a quantum field theory in a pure de Sitter spacetime, or what appears to be a reasonable assumption, is that along a Cauchy surface, sigma, which we take to be an S3 or R3, whatever, resides a quantum field theoretic Hilbert space. Yeah? So if it's a quantum field theory, it's a reasonable assumption that it has a quantum field theoretic Hilbert space that resides on the spatial slice. And we ought to be, given the symmetries of the problem, we ought to be able to decompose this Hilbert space into the set of unitary irreducible representations of the de Sitter group. Yeah? So it's a Hilbert space, there's a symmetry in the problem, there are a special class of operators in the algebra of all operators that furnish the de Sitter group. And it's a reasonable request that there's a Hilbert space. It does not conflict any of these issues, yes? And that we can organize the states, decompose the Hilbert space into the set of... But then we're tasked with understanding what are these unitary, these IREPs, yeah. And by good fortune, this was a problem that was solved by many mathematicians, but in its most general form by the work of Harishchandra, who classified rather generally for non-compact Lie group, semi-simple, I think, Lie groups, the set of IREPs. For specific cases, there was, of course, other people working on the problem, but the general theory, I think, belongs to Harishchandra. And so this is a problem that, at least for this, for the single cover of the group, is a problem that has been solved. Yeah, so there is an answer to this question of what is the space of unitary irreducible representations. And in fact, I think it's also solved for the double cover, although it depends to what degree of detail you demand that it be solved. For instance, if you require tensor products, that might not be completely classified. Okay, so that's the reasoning that will follow, and I hope this reasoning is clear. And so now we're tasked, so I'd like to give you a flavor of what do these IREPs that populate the quantum field theory de Sitter-Hilbert space, what do they look like, yeah? And so, questions before I proceed. Now, to develop this theory in detail would require a whole course, many books, but I think in the SO2,1 case, I can give you a flavor that is remarkably loyal to the general picture. But let me also give you a reference of a physics-friendly paper that does this. So let me give you a reference. If you discover that it is your calling to study unitary irreducible representations of the de Sitter group, good. But what I'd like to do is discuss the case of, I'd like to discuss the case of SO2,1, which is the two-dimensional de Sitter group, which, like I said, carries a remarkable amount of overlap with the SO4,1 case, but I can at least present in a mildly reasonable way in what follows. So at the level of the Lie algebra, this group over here, which you can think of as sort of the space of, one way to represent it is as 3x3 matrices that leave invariant the 3D Lorentz metric, yeah? So it's, okay, so here's a question to warm our brains a little bit. How many generators does SO2,1 have? Close, 3. SO3,1 has 6, SO2,1 has 3. Yeah. So at the level of the Lie algebra, it is isomorphic, and this is a nice exercise, if you've unfamiliar with it, to SL2R, where SL2R is the space of real valued 2x2 matrices, yeah, where they have a unit determinant. At the level of the group, SL2R is the double cover, I think, of SO2,1. But at the level of the Lie algebra, this is all good. And already one can mention a general thing, that given that the Lie group is non-compact, so I can already make a statement for you, the non-trivial, of course, is a trivial IREP, which is just the identity, just a simple, single, one-dimensional, trivial, irreducible representation. But any non-trivial IREP, unitary IREP of this group, will be infinite dimensional. Yeah?
Sorry, can you explain the double cover meaning in this setup?
Sorry?
Can you explain the double cover meaning?
Yeah, so
in
the
this
double
setup?
cover is basically a 2-to-1 map of the group where, for instance, here, this group has a maximally compact subgroup, which is SO2, sorry, yeah, which you would allow to take not just integer quantum numbers, but also half integer. So it's a double
Right, yeah.
covering. Yeah. Yeah.
So the difference is in the eigenvalue of the compact generator.
Exactly. Yeah.
In one group you have like 1, 2, 3 numbers, and the
Yeah.
other one is 1/2.
That's
one
right.
half.
And
Okay.
so this would be a way to allow for the quantum states of fermionic fields in the theory also. Yeah. Okay. Good. Yeah, infinite dimension. So we can already anticipate that unitary irreps, unlike the non-unitary ones, because non-unitary irreps will be irreps of the complexification of this group, which includes SOD+1, which admits finite dimensional irreps, are infinite dimensional. Yeah, so they're rather, they're very large representations. But in order to describe them, let me write down the algebra first. So we're going to have 3 generators, like I said. Yeah. And we have our the following algebra. Yeah, so these are our algebras. And just to give you a sense, the D over here is the SO1, 1 subgroup of SO2, 1. And so the SO2 is generated by L0, which is H plus K over 2. And it's convenient to introduce raising and lowering operators as well, which are given by the following, by the following quantity. Okay, and in terms of this generator, so L0 is a standard Hermitian generator. H, D, and K are standard Hermitian generators. L plus and minus are complexified generators of the group, but we'll use them as sort of ladder type operators. And the algebra, in terms of L plus, L minus, and L0 takes the following form. It's very similar to the raising and lowering operator algebra of SU2 up to signs, okay? And we have a quadratic Casimir as well, which is commuting with all other generators, which will define, whose eigenvalue we'll define, so now this is just the definition, to equal lambda times 1 minus lambda. Okay? So that's our algebra. And we'd like to study the unitary irreducible representations. And I note already that I've assumed a very specific hermiticity condition on the generators, which, for those of you who've studied conformal field theories, where you have things often like P dagger is equal to K, so this is not the hermiticity condition I'm studying over here. In here, I'm studying a standard hermiticity conditions. And this is an important distinction in how we treat the Euclidean conformal group from the point of view of de Sitter quantum field theory versus how we treat it when we study Euclidean conformal field theory, where we're really trying to anticipate the reality conditions of the Lorentzian theory in the Euclidean signature. So here, this is a kinematical group of a Lorentzian spacetime subject to its standard unitarity properties, and we're going to keep those reality properties as they are, which means in particular that L dagger plus is equal to L minus, yeah, L dagger 0 is equal to L 0, and so forth, yeah? Yeah. Ah, yeah, exactly. Okay, so now let me discuss the representations you may be most familiar with, which are representations that go under the name, we're accustomed to calling them highest or lowest weight irreps. But really in the de Sitter language, these are often called exceptional or discrete series irreducible representations, which carry an index, which has to do with lower plus or minus. And these representations are labeled by some parameter delta, which is good, which we take to be an eigenstate of the generator of the compact subgroup, which in particular means that delta takes integer or half integer values. Yeah. Okay, because L naught is a compact generator. And we will define a special state to be annihilated. We will define this state, delta, to be annihilated by L minus. Okay? So that's what's called the lowest or highest state condition. And on top of this state, we can act with L plus, yeah, to create, let's see how I label them. Yeah, we can act with n copies of L plus to create an infinite family of states parameterized by n, where n is 0, 1, 2, 3, 4, 5. Yeah? And this constitutes the simplest, perhaps, irrep of the theory, which is the highest weight irreducible representation. And we can lower and raise the value of n by acting with L plus and L minus. And we see that the representation is bounded from below for the lowest weight, or bounded from above by the highest weight, but it's unbounded in the other direction. So this is an example of an infinite dimensional irreducible representation in that it has an infinite number of states, which are conveniently labeled in a discrete basis by eigenvalues of the L naught generator. Yeah? And there's two of them, the highest and lowest weight. Okay? So that's an example of a bounded, infinite, unitary irreducible representation. And there's analogs of these irreps in DS4, yeah, that you can study. The only difference is that there's an additional label associated to these irreps in DS4, which has to do with the fact that one can label the states not just with respect to this delta, but also with respect to an intrinsic spin that has to do with an SO3 subgroup of SO4,1, that for the case of SO2,1 would be an SO1 subgroup, which, so what we lose in this representation theory is the dependence on the intrinsic spin. But this boundedness is there in these, and these generally known as the exceptional or discrete series irreducible representations of the de Sitter group. Yeah, so that's an example. But in addition to this example, there's another class of irreps that I'd like to mention, which are unbounded and in fact, in a sense, more generic. And they're called the principal series. And so let me discuss their properties for a moment. So I'm going to label these family of irreps again in a basis of states where M takes any integer value, yeah, not just positive or negative, any integer value, yeah, And lambda is some parameter that's associated, like I said, to the quadratic Casimir. Okay? And let me see how to organize this. So the basis I've defined is such that the L0 eigenvalue is m. That's the reason it takes integer or half integer values if you did the double cover. Yeah? But in addition to that, we can compute the following quantity. Ah, yeah. That's right. We can compute the following quantity, yeah, bearing in mind how we defined the quadratic Casimir. Yeah. So this is okay. So let's put this as a homework. It's a standard type of calculation, but I'll explain why this particular combination. You see, what we're doing here, because of the hermiticity properties of L minus and L plus, is we're computing a norm. And therefore, this has to be positive. Yeah? And what we used in computing this is the fact that the quadratic Casimir is simply given by these particular combinations of L plus and L minus. Yeah? And it's L naught squared. And we use the fact that our states are eigenstates of L naught. And so now, just by computing these expectation values and knowing that they have to be positive for all values of m, because it's a norm, yeah, we have a condition on lambda, on the space of allowed lambdas. Yeah? So the condition is that that this particular quantity has to be positive, yeah, which in particular implies that lambda has to take one of two possible forms. And so actually this is a nice real-time exercise. So let's see if people can anticipate what allowed values of lambda this equation enforces. Good. Lambda can exist between 0 and 1, and these values constitute what's known as the complementary series. So that, you've just identified a continuous family of irreducible representations of the de Sitter group that are labeled by this lambda and are unbounded. And they're unbounded, yeah, so here we're assuming lambda is not an integer, because if there was an integer, we may land in a situation where eventually we'll hit a lowest weight state. So here we're assuming lambda is not an integer and takes these values, yeah. But there's another one. There's another solution, which is a little trickier, but if lambda is equal to 1/2 plus I nu, then 1 minus lambda is related to the complex conjugate of lambda, yeah? And lambda times 1 minus lambda is equal to 1/4 plus nu squared, which is positive, yeah? And so, interestingly, nothing, you see, I chose this peculiar parametrization of the quadratic Casimir mostly because that's the kind of terminology that we use in conformal field theory. But from the perspective of our reality conditions and our hermiticity conditions, yeah, nothing requires lambda to be a real value, yeah? And in fact, these representations exist, they're unbounded, and they're labeled by yet another continuous parameter, which is nu is equal to some real number. And these are the famous principal series principal series irreps of the de Sitter group. And in fact, they're the generic representations. They're the non-special ones. So sometimes in the literature, it's stated that because of the complex conformal weight, there are unitarity issues with the description of de Sitter. Ironically, this object over here, which is complex value, is perfectly compatible and necessitated by unitarity. Yeah? And so there's nothing peculiar about it. What was peculiar, what happened is that we insisted on writing the Casimir in this particular form because that's what we're used to in the standard highest weight terminology, and we landed on a complex number. So these then, remarkably, this simple exercise exhausts, that I have not proven, but exhausts for SO2,1 the class of unitary irreducible representations. There are 3 flavors. There's the highest weight, discrete series plus, the lowest weight, discrete series minus. There's the complementary series where lambda has this unusual range over here, and there's the generic principal series irreducible representations. These two are unbounded in that m goes from the negative integers all the way to the positive integers, whereas the highest and lowest weight are bounded but infinite. Yeah? And of course, there's also the trivial representation. Okay, so are there any questions about that? And while I ask that, how are we doing for time? Yeah, thank you. No, I don't like ambiguous statements. Okay. Okay. So now, let's see what else I want to say about this. Yeah. Well, let me not, okay, so I hope it's clear. So then, let me phrase it in the QFT language. The Hilbert space of a quantum field theory on DS2 can be partitioned into a direct sum of these unitary reducible representations, yes, of normalizable states. So when we express them in this basis, these are normalizable states. What I made is an abstract statement, so but it will hold for this Hilbert space. And let me add a few more comments, which are that it's not only the irreps that we know for this group theory, and the analog is true, by the way, for DS4. We have the principal, we have the complementary, we have the discrete series, except, like I said before, that the discrete, so let me just state it. So we have the principal, which is labeled by nu, and the quantum number S, which has to do with the behavior of the SO3 subgroup, the analog of the intrinsic spin of a particle, if you will. Yeah. And nu is this nu, except here lambda is equal to 3/2 plus I nu for the principal series. Okay. We have the complementary series where, well, let's write it as follows. Pi tilde nu S, where now, rather let me call it lambda, where lambda now ranges from 0 to 3 instead of 0 to 1. Yeah, so this changes with the dimensionality. Yeah. So the Casimir, I should say, so the Casimir, so the unique quadratic, there's a quartic Casimir for SO1, but there's still a unique quadratic Casimir. In this case, we would have lambda 3 minus lambda plus S plus 1. Yeah, so that would be the Casimir of SO4,1, excuse me. So we have the principal series, the complementary series, and now I'm talking about the single cover of the group. And then we have a family of discrete series that's labeled by, again, a spin type parameter, but for each spin, there's another parameter t, which takes values from 0 to s minus 1. And these, for each spin, this family is known in the physics literature and the family of partially massless, irreducible representations. They were discovered in physics maybe the late 80s or so by people like Desser and Nepomniachtchi and Higuchi and others, but they were known in the mathematics literature since the 50s. And I should say that this is for the single cover, and quite remarkably, if you're also interested in half-integer spin, which we may wish to be interested in because we have fermions in nature, that good old property of nature. So you can have principal series also for half-integer spin. Yeah. However, complementary series are not present for half-integer spin, curiously. Fortunately, the discrete series are indeed present for half-integer spin as well. Okay, just a curiosity for you, in case you have this burning desire to know everything about. Well, this is the best, in a sense, the best language we have to classify the potential set of particle species in a de Sitter background. Okay, most of the standard model lives in the principal series. I think even the neutrino with the masses that we measure for it.
Dio,
yeah.
Discrete fermions are present in n equals 4 in 4 dimensions, you said?
In n equals?
In 4 dimensions.
For DS4, yes, you can have
Discrete,
fermionic discrete, unitary fermionic discrete series. But that's not a guaranteed statement in all dimensions.
Just in 2 and 4?
In 2, you have the analog that discrete series for the double cover. You can have delta also for half integers, so they're also there in that sense.
Right, so here in 2 dimensions you can have scalar fields with tachyonic and fermionic fields.
Wait, I'm making a statement about the algebra. So there exists IREPs, discrete series, both for where delta is an integer, but also a half integer, which I think is the statement. So DS2 and DS4, in fact, share these type of properties. I think there's a question further back.
So does the two-dimensional de Sitter have like this algebra does have a Verma module kind of a structure, and then we can maybe find the null states as well?
There are no null states in this algebra, but they are analogous to sort of this.
Similarly, in the 4D, in the 4-dimensional de Sitter, can we have? So I'm trying to understand how is it different from the conformal algebra in 3 dimensions.
No, they're the same algebra.
Right.
They're the same algebra, and these are the highest weights. So the discrete series are the ones that you're familiar, which is the highest weights. And indeed, they're linked together by a finite IREP that lives in a kernel that you could call sort of a set of states that you want to quotient out, and that's what splits them. They would otherwise be joined, the highest and lowest weight. But the principal series have no null states and no such kernel structure. Now, we don't study, and a question you may want to phrase it is, why don't we study the principal series? But in fact, it depends on the question we ask. If we were doing harmonic analysis of the Euclidean conformal group, and we were interested in decomposing a group-valued function on a complete basis, we would have to confront the principal series. What happens is that we're often physical in a Lorentzian continuation of the physics, and for that, we deform contours in such a way that we pick up bounded representations with good positivity properties, because for the Lorentzian conformal group, we have SO2, 3, and the SO2 is a Hamiltonian. And so it's a physical condition, and the association to the Lorentzian physics that forces us to select these particular representations, and also the fact that we study the universal cover of the group. And that allows delta not to necessarily take integer values, but also more general values. And so that's what happened along the way. Yeah. Okay. More group theory. Yeah, let's do more group theory. So well, a nice exercise is to compute, well, I related these to quantum fields yet, but to see what are the standard model fields in terms of what is the representation content of the standard model in de Sitter. But the mathematical understanding of these groups goes beyond just the classification of the AREPs. For instance, although I cannot guarantee you that this problem has been completed, very much is known about the tensor product structure of these AREPs. And already remarkable things happen. And in the quantum field theory language, if you want, these AREPs would be furnished by what we would ordinarily call the single particle Hilbert space of the quantum field theory. And the tensor products would encode the content of multi-particle Hilbert space, where we take tensors, products of the single particle Hilbert space. And for instance, let's go back to SO2, 1. This problem was solved in papers of Repka, among others. For instance, one has that the tensor product of two, well, let me write it. Principal series contains in it principal series and discrete series irreducible representations, rather remarkably. In higher dimensions, this statement remains true, provided they carry some intrinsic spin, but not if they're spinless or spin a half. And similarly, the tensor of two discrete plus or two discrete minus is coded entirely in terms of a discrete plus or discrete minus, which is another reason that we were protected from the principal series in the conformal field theories that we're familiar with. However, the tensor product of discrete, plus and minus, if my memory serves me right, can contain the whole set, yeah? So, on the other hand, it's quite hard to generate complementary series in the tensor product of non-complementary series. They're kind of special, isolated, interesting feature. But much is known about the tensor products, and not just for SO2, 1, but also SOD, 1, and also the spin, the double cover of spin 1, 4. Although I'm not sure if the exercise has been completed. There may be a few exotic representations that in the double cover of the groups that are still unknown. And that's a nice target if you're mathematically minded to see where that's at and complete it. Okay, and finally, a very useful way to represent the content of a given AREP is in terms of the character, the group reduced group characters. And indeed, maybe that's another nice homework problem. So one way to discuss the content of representation would be, well, let me take the trace in a given AREP, labeled by lambda, of a particular exponentiation of an element yeah, this T is not necessarily time, it's more viewed like a chemical potential. Times, say, the generator of SO1, yeah, so this is a very typical type of group character that you may wish to compute. So you're in the IREP, so you can represent the generator is some sort of infinite dimensional matrix whose trace, and you may wish to compute the following trace, and as you vary T, you explore the content of the representation. And for instance, again, this were computed, we can call them, if you want, Harishchandra characters. And just to give you a flavor of what they look like, so let's take the principal series IREP, yeah, in SO2,1. But the same will be true more generally. So this character will take the following form. It'll look like e to the minus t 1/2 plus I nu plus e to the minus t 1/2 minus I nu divided by 1 minus e to the minus t. That's for SO2,1, yeah? So it's a very sort of simple function, yeah? If you're familiar with characters in the ordinary conformal group, you'll see that this one has a contribution for what people would ordinarily call the shadow conformal weight, in addition to the standard conformal weight. But that doesn't matter. This is the character, and one can also express it in terms of a Fourier decomposition. Sort of this is a non-compact generator whose spectrum can be decomposed in the reals, so here omega. However, there's a measure, a non-trivial measure in the space of eigenvalues, which is this rho of omega, which is it's a nice function, it's a meromorphic function. With simple poles in the complex omega plane. Which are sort of regularly spaced on either side of the real axis. I think this is plus or minus nu, and then actually, well, let me know. It's a meromorphic function, anyways, that well, whose pole structure is effectively sorry, it's just downstairs. Yeah. Is captured in a regular spacing in a complex plane. Yeah. So, and in fact, characters again are known for many of these representations, and we'll come back to this character later on because it'll play a role in some of the physics of the static patch. Yeah. But okay. So that I think is the group theory I wanted to discuss, and so. At least given this rich group theoretic structure, we can try to organize properties of quantum fields in de Sitter, yeah, and states. And to give you an example, a topic that was explored in early work of Broshebstein and Moskela and has been revisited more recently. You can, for instance, try to decompose the two-point function of an interacting quantum field theory in de Sitter in terms of the two-point function. So this row is not to be confused with that row over here. So let me write it over here. In a Challen-Lehmann type representation for the free two-point functions of quantum fields, but in where this spans the UIRs. Yeah, so this is a way to organize. Oh yeah, so in fact, it's just a way to decompose an interacting two-point function of a quantum field theory. So the general task that one is required to do, imagine you have a scalar field theory, yeah? Imagine you have a scalar field theory and you're interested in calculating some, with respect to some time ordering, an interacting two-point function in the theory, yeah? And you may wish to express this two-point function in a spectral decomposition, what's called a spectral decomposition. And so, sorry, x and y here represent two space-time points in the manifold. And so one way to proceed, yeah, and this is a discussion that you can find in many different texts, is to insert a complete, yeah, a complete set of states, so add a resolution of the identity in the interior, yeah, lambda, where lambda spans a complete set of states in the quantum field theory Hilbert space, yeah. And then what you're left with, so I'll give you a very schematic sort of perspective of this object. Is sort of a decomposition of the two-point function in the following form, where again, this is the interacting vacuum of the theory, but we assume that the vacuum respects the symmetries of the problem. So in de Sitter space, this would be a de Sitter invariant vacuum, and in Minkowski space, this would be a Poincare invariant vacuum. And what one can accomplish using the symmetries of the problem and the fact that this basis that you're decomposing in is a basis that transforms nicely under the kinematic symmetries of the group. So in de Sitter, these would be a complete basis labeled by the irreps of the de Sitter group. In the Poincare, these would be standard eigenstates of the Poincare generators, yeah, and transform nicely under the Lorentz boosts. So what you can do is you can write down an expression for these quantities in terms, since they have to hold for all theories, it's group theoretically fixed, you can write down these quantities up to over all coefficient in terms of their free values, yeah? So essentially these are free, the field modes labeled by whatever quantum numbers there are of the free theory, and similarly here, yeah, and we have access to these by studying just free quantum field theory. And so effectively what happens is that you can decompose the interacting two-point function in terms of a function of whatever this label across the span of irreps is, times effectively the modes, the sum of modes of the free fields, but that's nothing other. Of course, I'm overlooking issues that have to do with time ordering. I didn't think I was going to derive the Cullen-Lehmann for you, but that's okay. But this up to time ordering, and here we're choosing the Whiteman function, so it's the not unordered correlator. It's just the free, it's just the mode representation of the free two-point function in a given irrep, lambda. So all this to say is that the spectral decomposition that represents sort of an interacting two-point function in Minkowski space has an analog given this decomposition of Hilbert space in de Sitter, but there's some interesting differences. For instance, in Minkowski space, the typical structure of this spectral density, maybe you've seen this plot in QFT courses, so it's positive by virtue of the fact that this is the absolute value of c squared, but it typically has a structure where it has some delta function that's isolated, Yeah, so this is the rho lambda, absolute value lambda square. And maybe if the theory admits bound states, there's some few others. And then if the particle has mass m, roughly around m squared, 2m squared, you start to hit a continuum of states which has to do with the multi-particle behavior. So that's the characteristic a sort of spectral decomposition that comes out of a Cullen-Lehmann representation. And it's interesting because if you happen to have in your hands an interacting two-point function, you can spectrally decompose it and see what kind of resonances the theory or bound states the theory exhibits. And in the case of de Sitter, it's a little different in that this structure is completely washed out, and instead one has sort of a continuum almost from the get-go of representation. So this idea, and it has to do with this basic issue that there's no conservation of energy in de Sitter and no sort of natural way to organize things in terms of, only when you have sufficient kinematic phase space, like more than twice the mass of your single particle states, can you start exciting the continuum. Everything is much more of a soup in de Sitter space. Yeah.
Here,
okay. Yeah.
Here you would use only the discrete series?
No, in general, you have to use, it's a complete set. So you're inserting the identity, so a priori you have to put the complete set decomposition of the Hilbert space, and it's, what contributes, of course, depends on the theory. It could be that in some theories it's only the principal series, and in others it could be other things that appear in the unitary reducible representation decomposition. Yeah. Okay, this completely disoriented me. Anyways, spectral decomposition, interacting two-point functions, good thing to know. Right. Yeah, so what I wanted to say, the last point I wanted to make is so I've given you a rather abstract description of these representations, and it is at least a reasonable demand from your side that I give you an association of these irreps to particles, or fields, better said, in de Sitter. And in particular, let me give you the following imperfect map. So the principal series with this parameter nu correspond to particles which are sufficiently massive fields in de Sitter, where this lambda, so in DS2, just to give you a flavor of what it looks like, this nu parameter is equal to something like the mass squared times the de Sitter length square minus 1/4. Yeah? So massive fields, massive with respect to the de Sitter length scale, dimensionless statement, massive fields furnish single particle states of massive fields, free massive fields in de Sitter furnish the principal series irrep, yeah? And in that sense, they're generic, it's sort of the heavy particles. And then light fields correspond to the case where the mass of the particle is of order 1 in de Sitter units, such that nu becomes imaginary and suddenly lambda is in this real range. So that's the complementary. I don't know how I labeled it. How did I label complementary series? With a tilde? Yeah. And finally, gauge fields and their partially massless cousins, which are also gauge fields, transform in the discrete or exceptional series. Yeah? So you can anticipate the types of particles that you have, and they each, when free, are associated to one of these irreps. However, like I said, this map is incomplete, And we do not have, for all known irreducible representations of the de Sitter group, a free field realization. This would be a nice target to prove or disprove. It's the analog of the Wigner's hypothesis that relates elementary particles to unitary irreducible representations. And there are many exotic irreducible representations of the de Sitter group that we do not know whether they really do admit a local unitary free quantum field theory realization. So there's a nice target and just gives you the flavor already at the level of QFT in de Sitter that there's work, very concrete work, that is remaining to be done. Okay, so yeah. Okay, so let me end it with that comment, and then we can do the questions before moving on to the next topic. Yeah. 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 But I'm allowed to take this off now? Thank you.
Thank you for the lecture.
Thank you.
So, okay, of course, you, on the beginning, you said that you were constructing a Hilbert space.
With the what?
You said you were constructing the Hilbert
Yeah,
space on closed slicing of de Sitter.
Yeah.
Okay, so of course the group is the same, but does something change if I try to construct this with a flat slice or an open slice?
No, no. So you're entitled, provided that the slicing you pick obeys the de Sitter symmetries. Of course, you could be in a situation where you take a quotient and you break the de Sitter symmetries. And then it's a different story. So this torus, for instance, you've broken globally the de Sitter symmetries and you have to be careful. But what you will, if you have non-compact slices, you will have to be a little bit careful because there your states will not, in the natural basis, which would be the momentum basis, they will not be normalizable, but rather plane wave normalizable. And so I find it convenient to discuss the Hilbert space in the compact space because when they're labeled by the quantum numbers of the sphere, your Hilbert space is organized in a normalizable basis. That's the only thing that you have to deal with, this plane wave delta function type normalizable Hilbert space.
Okay, but I don't know, there's some interpretation that changes at least? Because it appears to me to be really different if I do quantum field theory in something that changes with time or something that is static, for example, like you said in the beginning.
In the static patch, the interpretation changes because now you're only talking about a portion of the space-time. And so there it changes because you have to talk about a density matrix. So the Hilbert space here we're talking about, these are pure states that live on the full slice. But if I'm in a portion of the space-time, I may have to talk about a density matrix. And then I have to discuss things in a mixed state rather than a pure state. Yeah.
But that doesn't happen if I have like, because the flat slicing
No,
you also
the flat
have like
slicing,
two
these are still
spaces.
complete slices provided you specify clear conditions at infinity. So this is a complete spatial slice, you see, provided your fields obey conditions here. Whereas this is not. Yeah.
Thank you.
Yeah.
Hi. I don't know if my question is too naive or if I missed something, but you have the dilation, okay, the subgroup respect dilation. So you can, I can think like something like radial quantization, and this dilation makes some, looks like a Hamiltonian, representation of the group, okay? But the eigenvalues of the operator now has complex numbers.
Yeah.
So where is unitarity and locality?
Well, that's right. So that would be the way we would treat a Euclidean CFT that would later continue to Lorentzian signature. And then the radial quantization would correspond to unitary evolution in Lorentzian signature. But here, we are never continuing the spatial slice to Lorentzian signature. So the unitary, so what you're saying would require us to do things like P dagger equals K. The unitarity here is coded in the fact that we have different reality properties on our generators than the ones that we use when we do radial quantization. So it's a different reality conditions of the generator. This is the important point. That's why we're allowed to have complex conformal weight in this problem. Yeah, it's a good question.
Well, thank you very much for the lecture. What I'm curious about is that SO2,1 is also the Lorentz group in 3 dimensions. So I'm wondering whether
Sorry.
interpretation as
Yeah.
particles in
Yeah.
1 dimension less.
Yeah. So you're asking, is there room? So there's an ongoing effort right now, in fact, for people to recast a lot of Minkowskian physics, which traditionally is expressed in terms of an eigenbasis of the translation generator of the Poincare group, in terms of eigenbasis of the Lorentz group. And there's a very nice map between the two, which is a type of what's known as a Mellin transform that maps one representation to the other. And indeed, these representations appear when these principles, when people try to recast the asymptotic Fock space of Minkowski in the Lorentz basis. This is the celestial people. They are doing these things. Yeah.
Thank you.
But just for me to understand, but there is any unitarity bound should have an unitarity bound.
The unitarity bounds that you get in the sitter, well, first of all, if it's complex, it's not going to be a type of unitarity bound that you have in mind. But like I said, the unitarity bounds that you have are, for instance, the fact that lambda, when it's real, lives between 0 and 1. If lambda was 3.2 or minus 4.8, that would not be allowed. So that's a unitarity bound.
Okay.
If you have lambda as 3 or 14 times pi plus I nu, this would also not be allowed. So there are restrictions, of course. Or when it's an integer, it's an integer. It's not an integer plus epsilon, it's an integer. And so this is the kind of unitarity bounds that you have instead. They're much more elaborate. And another beautiful thing about the de Sitter group compared to the ADS group is that it really changes when you change the dimension. For instance, the DS3 group has no discrete series, but DS2 and DS4 does. Yeah? It's a wild world. Yeah.
Okay,
Yeah.
thank you.
What? Yeah. It's a very rich group.
I have a question, if I can lend you some time.
Where's my water? Yeah.
Do you need water?
No, I found it. I had just lost it.
Guy told us,
Unitarity. Yeah.
Guy told us a couple of days ago that he's looking for light fields in the. He has these light fields at the end of inflation, and
Yeah.
he computes backwards these diagrams.
Yeah.
But you mentioned today that the I forgot. What is the pi tilde name of the
Complementary series.
The complementary is typically hard to mix with the other ones.
Yeah.
Like, okay, so if I mix complementary with complementary, do I get
Yeah.
principal or do I get
Good
something else?
question. Yeah, I can't remember off the top of my head. I think you get principal plus complementary. Yeah.
Okay, that's good news. Because
Well, but don't quote me. Switch off the camera because I can't remember.
no, okay, but suppose you could show that complementary doesn't mix with the others, that would be a problem for Guy's
No,
talks.
because he's slightly broken the de Sitter group anyways because of his
okay.
low role of inflation. And in
Okay.
the de Sitter limit, this would become a strictly massless field, which is a very even more special representation in a sense, because you see here, there's a difference between this and this.
Yes.
Yeah, and so it's
Okay.
more elaborate than that. In fact, the strictly massless free particle in de Sitter is really not in the Hilbert space as a free quantum field theory because it's not quite normalizable, the de Sitter invariant state. So you have to turn on interactions, but when you turn them on, it gently pushes it back to the complementary.
Is it similar to the massless fields in 1+1?
It's similar to the massless fields, massless shape, but it's strictly the massless case. So there you have, well, of course, there you can make it a compact field, and you can try to play that game. Yeah.
Okay.
But there, the operators would live in with the derivatives of the field, so then they would still, the physical states would be furnished by other representations.
Okay, thanks. Further question? I have lent you plenty of time to think. Okay, if not, we thank Guy again. Dio.